Hi everyone, I'm Jenna,
And I'm Steve.
and welcome to another Field Trip Friday. Where are we today, Steve?
We're here at Duke University,
Yeah.
and we're in the Fitzpatrick building, which houses the Shared Materials Instrumentation facility.
Yeah.
And that's a place where we're going to visit and learn how they make and look at really tiny things, like amazingly, astonishingly cool tiny things.
That is so exciting. Let's go look at some tiny stuff.
Let's do it.
So my name is Talmadge Tyler, and I am a research and development engineer here at Duke University in what we call the Shared Materials Instrumentation Facility, or SMIF.
Cool.
That's awesome. And so what kind of work does that entail? What do you spend your days doing?
So in SMIF, we do a number of things. It can be broken into two main categories. One would be considered fabrication, so where we make things, and we'll show you an example of that in the clean room. And the other would be characterization, so where we're looking at things, measuring things, figuring out, various properties of materials or devices. So fabrication and characterization. I'm primarily on the fabrication side, but I do a little bit of both.
Cool. So you're holding something that you make here. What is that?
So this is just one of any number of examples of devices that we can actually fabricate or make in the Shared Materials Instrumentation Facility. So this device here is actually what's called a photo detector. So photo means light, so it's a light detector essentially. And this is made with a number of process steps that we do in the clean room. This particular device is part of a research program that was conducted here at Duke University in collaboration with the medical school. So this is actually a medical device. It's used to measure light that's coming off of tissue. So this is a way to characterize human tissue. And to make a long story short, this was developed for the purposes of distinguishing healthy tissue from cancerous tissue. So this is in the whole larger scope of cancer research. But this particular device is part of that. So this is actually ongoing research here at Duke.
Hi, Holly.
Hi,
So,
welcome.
thank you. What do you do here at Smith?
I am a research and development engineer here at Smith. I do a lot of characterization, which is looking at tiny stuff. I also run our outreach program. So part of what we want to do is to bring the science that we do not just to the scientists, but to everybody, like all you guys who are watching today and you guys visiting.
That is
Thanks
so
much.
cool.
Yeah, that's really cool.
Can we take a look?
Let's do it. Okay, there's our
Cool.
sample loaded in. We're gonna close the door. And we're gonna start pumping the air out of the chamber, because an electron microscope has to work in a vacuum.
Cool.
Because electrons are so tiny that if they hit air molecules, they'll
They'll-
actually bounce off of
Right.
them, right? And they won't make it all the way to the thing that we're trying to emit. So right now we're at 40 times bigger than real life, so 40 times magnified. We also have down here a scale bar. So the scale bar tells us how big something in the picture is in real life. So right now the scale bar is 2 millimeters, which means that in this picture something that's this long is 2 millimeters.
Ah, cool.
So we're gonna start zooming in here.
It's really cool. You can just kind of point and click zoom.
Right? I'm gonna give us a little skinny ends of these. There we go. You can see the rings too. And I'm going to adjust the brightness and contrast a little bit because it's very bright there. There we go.
Oh, cool, yeah.
I'm going to adjust the focus a little bit so it's a little bit better in focus. Some of our microscopes you have to do this
Manually?
manually. This one you can do it by hand. So now you can see much more sharply these edges.
Yeah.
So you see that they're not actually perfect.
Yeah, you can really
As
see
much
that
as we tried to make them,
they
right?
look
As
really
good as
perfect
we
there.
could.
One, yeah.
But as we zoom in, so now we're 1,000 times magnified. The scale bar is now 100 micrometers. So micrometer is 1,000th of a millimeter. And that also happens to be about the width of one of your hairs. So if you took one of your hairs and looked at it, the width across the skinny way is about this big. So these lines are way skinnier
Right.
than the width of one of your hairs. And if we move, let's go. Here you can see a little bit better that interface between the two different materials. So you can see that the material that makes this part is a little bit different than the material that makes this part. This is a little bit harder to see in this view. So what I'm going to do, readjust the contrast there a little bit, and I'm going to make this go slow. So scanning electron microscope means that the electron beam is actually scanning over the surface. And so how fast it scans determines how good of a picture we get, right? So when I started, it was moving fast, which makes it easy to move around and find the sample and zoom in and out. But if I want to take a really pretty picture, I want to slow it down. The slower I go, the less noise you see in the image. You see how much clearer it is here than it was before. And so if we zoom in a bit more, we'll go slow now. So we're now 3,000 times magnified. Our scale bar is now 30 microns. To give you an idea of something that's 30 microns, one of your skin cells is about 30 microns. So that's about the size. In this picture, this line is less than 30 microns, so less than one skin cell across, right? So we're making things with really, really tiny little features, and you can see that there's some debris on here, right? So this hasn't been in the clean room for a while. We had it open in the hallway to look at, right? So this is the kind of stuff that can get on there that can cause problems with some of these devices.
Bake the wafer here for a minute.
Yep.
We're going to take it off and bring it over here. Load a photomask and expose the wafer here. It takes about 30 seconds. Then we're going to move over here in this chemical for 60 seconds. Rinse it in the water, dry it off. It's done at that point. And then we'll probably come here to the microscope and look at what we just made.
Cool.
Okay. That's worth looking at, I think. We know what these are because we measured them just a little bit ago. You can see the entire rate. These are 5-micron lines.
Wow.
Those are openings in the resist. This is photoresist. This is where it's open.
Right.
Okay. If we were going to do some etching, and this was an etch mask, we would etch into those areas.
Right.
If we were going to do some kind of lift-off metallization process, we'd evaporate metal into those openings.
Yeah.
Then we would dissolve everything else away, and we'd
Leave
be left
those
with little
traces.
metal lines right there. That's how
Yeah.
we produce patterns into the silicon or onto the silicon or whatever it is you're making.
Yeah.
Okay.
That's
So
cool.
it's done over and over and over again in making any kind of device you're making. Here, most people are not making integrated circuits with transistors. They're just not doing that here. They're making typically optical devices, microfluidic devices, metamaterials devices, but typically not fabricating transistors.
Interesting. Okay.
Right. This is a clean room that's made in many ways just like a semiconductor or computer chip clean room. It has most of the same kinds of equipment in it. It's just that people are using those processes and those pieces of equipment to make small things that just don't happen to be integrated circuits.
Right.
Right? They're doing the same processes to make new and novel devices.
Oh, that makes sense.
So the science behind this is similar to a solar cell, so a silicon solar cell that you would use to generate electricity with sunlight. The same physical process that's happening, light energy is hitting a material and it's creating electricity. That's happening in this photodetector. This just happens to be built specifically to detect light from tissue, but the science, the physics behind it is the same.
That's so cool. It seems like that's kind of a common theme at this in this space. I mean, in research in general, but particularly at Smith, there's a lot of like kind of reimagining how you might use a tool to do something different. We were learning with Holly that you can use an electron beam to actually look at something, but then when we were in the clean room, we actually saw that you can use that same kind of electron beam to fabricate something.
Exactly. Yeah, I think there's a lot of creativity in science, and like you said, reimagining things, sort of reinventing something, repurposing something. So yeah, there's a lot of creativity. I think scientists sometimes get a bad rap in the sense that they think, oh, science isn't terribly creative, the arts are creative, but I think there's a lot of creativity in science and engineering as well.
That's so cool. Well, thank you, Talmish. I think that was like just a really cool survey of so many pieces of the impact and importance of photolithography, but also of kind of one of the things that's been really cool in visiting your space is the relationship between different both scientists, scientific processes, and different research questions. And so seeing the facility and the space that you have to kind of take on those questions, like people can come here and they can start to invent things, they can start to analyze things, they can start to break ideas down into their component questions and really dive in. And it's so cool that you have a facility to do that.
Absolutely. And I think that's one of the strengths of a facility like this. One, our staff is quite diverse in terms of our education background and our strong or our areas of expertise. But we also get a wide variety of users. So we have from almost every imaginable discipline. So you can think of physics, chemistry, medicine, anthropology, even the arts. We have folks coming that want to characterize maybe old historical artifacts, things like that. So the variety is one of the reasons why this, working in a facility like this is so rewarding.
Yeah, it's been such a pleasure to visit it. So thank you very much for having us.
Yes,
Yeah, my
thank you
pleasure.
so much.